All right, today we're decoding the official blueprint that's designed to shape Sri Lanka's next generation of tech innovators. And let me tell you, this isn't just some school's syllabus, it's a real roadmap for the future. Okay, so what we're looking at here is the real deal. This is the official document from Sri Lanka's National Institute of Education, and it lays out the entire ICT curriculum for grades 12 and 13. You can think of it as a detailed map for any student who's about to step into the advanced world of technology. So, we're going to break this down into 5 parts. We'll start with the big picture vision and then get right into the nitty-gritty of how our digital world is actually built. All right, so what's the big idea? I mean, is this just about teaching kids how to use a computer? No way, not even close. See, this curriculum goes way beyond just learning a few pieces of software. It's really about building a pipeline of talent, for universities and for the industry. The real goal here is to empower these students to become the next innovators and problem solvers, the ones who are going to tackle the big challenges we're all facing. Okay, so let's get right down to the fundamentals. Because if you want to build anything in the digital world, you absolutely have to understand the basic language that computers speak. And it all starts with this one concept: data. The best way to think about it is like the raw ingredients for a recipe. Just a pile of numbers, some text, maybe some signals, but with no context at all. By themselves, they don't really mean much. And this is a really key distinction the syllabus makes right from the get-go. See, data only becomes useful information after you process it and give it some meaning. So, for example, the number 15, that's just data. But the average temperature is 15 degrees Celsius. Now that is information. That's something you can actually do something with. So the question is, how do computers actually see all this data? Well, they see it like this: just a long series of ones and zeros. Every single piece of information, every command you give it, it all gets broken down into this fundamental language, binary. And this is where it gets amazing. These super simple logic gates, they are literally the building blocks of all computation. I mean, think of them as tiny, tiny little switches. When you combine millions or even billions of them, they let a processor do every complex calculation you can think of, from just adding 2 numbers together all the way to rendering an entire video game. Okay, so once those fundamentals of logic are in place, the curriculum starts to build the machine itself. This is where we get into that fascinating relationship between the physical hardware, the stuff you can touch, and the software that actually brings it all to life. And what's cool is that students get a real sense of history here. They trace the incredible evolution of computing. I mean, we're talking about a journey from these massive machines that filled entire rooms, all the way to the devices we carry in our pockets that are, thousands of times more powerful? It's mind-boggling. Now, this right here is a core concept. It's called the von Neumann architecture, and it is the elegant blueprint behind pretty much every computer ever made. The huge idea here is that the instructions, the program itself, can be stored in the exact same memory as the data. And that flexibility, well, that's what makes a computer a general-purpose machine. And this is basically the bridge between all that complex hardware and, well, you, the user. The operating system, it's like a master conductor of an orchestra. It's managing all the computer's resources, everything from memory to the CPU, so that you can run your apps without even having to think about the millions of calculations that are happening every single second. Okay, and this is a really crucial point. Students aren't just learning about technology. The whole point is that they're being trained to create with it. This is really where all that theory starts to meet practice. I mean, just take a look at how the teaching time is split up. You can see the heaviest emphasis is on those practical, hands-on, creative skills. You've got 74 periods for programming, 68 for systems analysis and design, 60 for web development. The focus is clearly on building things. We're talking applications, websites, entire software systems from the ground up. All right, and for the final piece of the puzzle, the curriculum zooms way out. We go from looking at a single machine to this massive global network that connects billions of them. And it also starts to look ahead to what's coming next. So this is where students learn what's really happening behind the scenes when you, say, send a message or stream a video or just pull up a website. They get to dive into the protocols and the infrastructure that make all this global communication possible. Everything from a simple local network all the way to the backbone of the entire internet. But, a syllabus like this can't just be about the technology we have today. That would be outdated in a year. So a huge part of this is preparing students for the technology of tomorrow, which, as we all know, is changing and evolving at an incredible pace. And so the curriculum makes a point to cover these emerging high-impact trends. Students are getting introduced to the very concepts that are defining our future right now. Things like the Internet of Things, or IoT, the incredible power of cloud computing, and that huge challenge of how to make sense of big data. And when you step back and look at the whole thing, that really seems to be the core idea behind this entire blueprint. It's not just about teaching specific skills. By focusing on these fundamental principles, logic, system design, problem solving, the goal is to create adaptable thinkers. Because the big question isn't just, what do students need to know today? It's, how on earth do we prepare them for a future and for jobs that we can't even imagine yet?